Today, we shall look into the different factors that affect a spectral transition. Now, a spectral band is formed when atoms or molecules they move from a particular energy level to another energy level. So, if we consider absorption, atoms or molecules in the ground state may absorb energy and get excited to move towards the higher energy levels. So when they move towards the higher energy levels, they will absorb a finite energy of the value E2 minus E0 here. So delta E will be equal to E2 minus E0. Delta E will be equal to H into delta nu. And that particular frequency, delta nu, is represented by this spectrum. Here, in the spectral plot, we take wavelength in the x-axis. Hence, we get delta lambda as the plot. Due to delta lambda, we understand that this spectral line will have a width. It has a spectral width. Now, this spectrum is characterized by its position. Position represents its wavelength, lambda. Then it is characterized by its width. The spread of that spectrum is represented by lambda 1 minus lambda 2, difference between the half width points. And the other characteristic feature of the spectrum is its intensity, that is the amplitude of that particular wavelength. Now, one of the most important factors that we need to consider in a spectrum is its signal to noise ratio. It is the ratio of the amplitude of the signal to the amplitude of the noise. Now, what do you mean by signal and noise? Signal means the amplitude of the wanted signal, the wanted frequency or the wanted wavelength. The amplitude of that particular wavelength is called the signal. Now, by noise, we mean that any other wavelengths that come into it, other sounds that we do not prefer, or other light sources that we do not prefer, or any other waves that we do not prefer to enter into that detector. Electrical waves can also enter. So, those are all noise. So, here we say that in order to understand the signal, or in order to give the correct importance to that measured signal, the noise in the environment should be very small. So the signal to noise ratio represents the relative importance of that measured signal compared to the noise in the measurement or in the background. And in order to detect the real sample signal from the instrument noise, the intensity of this signal should be 3 or 4 times greater than that of the noise. That means the S by N ratio must be 3 or 4. In this plot, we can see that here the baseline is almost in this line. It is nearer to 0.5, the spectral power. Baseline is almost here. And from there we see a lot of peaks. But it is hard to identify which peak is relevant to the signal. Here we have this larger peak. We can understand that may be significant here. It may be a significant wavelength. And this one at 0.1 frequency, this may also be a significant signal. It may be, we are not sure. But these signals at nearer to 0.25 and here nearer to 0.28 and here nearer to 0.31, we are confused whether these are the signals or whether they are the noises in the instrument. So in order to clearly identify between the signal and the noise, we should have the amplitude of the signal as shown here to be almost 3 or 4 times greater than that of the noise in the background. Here we can see that the noise is just a very small fraction. There will be noise in the signal, in the detector, so we cannot completely remove that noise factor. So here what we do is we increase the contribution of the signal. Now another factor that can improve the spectrum is its resolving power, the resolving power of the detector, the resolving power of the spectrometer. Now, the resolving power is defined as the ability of the spectrometer to produce separate frequency spectra. If you remember properly, in the spectrometer that we use in the lab, we can see the different spectra while observing white light through the grating. In those spectra, we had a difficulty of viewing the yellow 1 and yellow 2 lines of white light, and in order to resolve them, we used to adjust the width of the slit. So by reducing the slit width, we can increase the resolution of the spectrum. Now, the resolving power, it is a measure of the performance of the spectrometer. How well does the spectrometer perform? And that depends on the exit slit width. So a narrow slit is suitable for better resolution. But what happens here is when the slit becomes narrower, the amount of light passing through will also reduce, and the intensity of that spectrum will decrease. So there we won't be able to view the second order spectrum if the amplitude is too low. So we make a compromise while adjusting the slit width, that we don't make it so narrow, we just make it narrow such that the enough spectral lines are just resolved. Okay. And then enough light would also be passing through it. So here a compromise is maintained between the signal to noise ratio and resolving power. Now, here in this picture, it is clear when the resolution is low for the spectrometer, we can see the spectrum only as shown in the black line. But when we increase the resolution of the spectrometer, actually there were two spectral lines in that common peak. So if the resolution is lower, we will not be able to distinguish these two wavelengths. Now, the two most important features of the spectral line are its height or intensity and its spectral width. Now, ideally, we expect the spectra to be a particular line showing only that particular wavelength. But in practice, when we take readings, our spectra will be broadened in width. It is due to several factors. Let us go through it. One of the factors is collision broadening. So in the sample that we take, in which we want to measure the absorbance or the transmittance or the emitting light emission, in that the atoms or molecules, it may be in the gaseous form or in the liquid form, and they will be in continuous movement, and hence they will continuously collide with each other. These collisions, they affect the outermost electrons of these atoms or molecules. So the outermost valence electrons, they will be excited to higher energy levels, and after their lifetime they will de-excite to their lower energy levels. In this excitation and de-excitation, they will emit radiation. It is usually in the visible region or in the ultraviolet region. Okay, so this collision has in effect affected the energy levels of the outermost electrons, and that energy levels happen to broaden. It is not a single discrete line. That energy level then becomes into an energy band, and hence this leads to the broadening of the spectral lines. Thus, we say that the collisions thus shorten the lifetime of the excited states and then lead to the broadening of the associated spectral line. Now, when the molecular interactions are stronger, we get more broadening. That is why collision broadening is dominant in liquids. The next factor that affects the spectral width is Doppler broadening. Now, by Doppler effect, we understand that the frequency that an object emits is modified due to its relative speed to the observer, or here the detector. Now, if we have the spectrometer trying to view the spectrum, if the samples in the if the atoms in the sample are moving towards the spectrometer, its relative frequency will be observed to be decreasing. Now, if the atoms in the sample are moving away from the spectrometer, its relative frequency will be observed to be increasing due to this Doppler effect. Hence, due to the random movement of these atoms or molecules, these particles show Doppler shift. The motion being random, the shift can occur both in the lower and higher frequencies. This effect, the Doppler broadening effect, is dominant in gases. Now, in order to remove this effects due to Doppler broadening, what we do is that we uh, investigate our sample by placing the detector at a 90-degree angle to the direction of the incident source light. That is, the detector will be placed perpendicular to the sample or the incident source light. Now, the next factor affecting the spectral width is Hasenbergs uncertainty principle. Hasenbergs uncertainty principle has different pairs. We are familiar with the position momentum pair. Another pair is the energy and lifetime pair. So here, according to this principle, we understand that it is impossible to simultaneously make accurate measurements of both the energy and lifetime of a particle. Delta E shows the energy change and delta T shows the lifetime of that particle in the two states. So according to Hasenberg's uncertainty principle, delta E times delta T can be greater than or equal to h by 4 pi. Now let us consider the electrons in the ground state. Their lifetime is infinity. It will always tend to stay in the ground state, right? Now if the lifetime is infinity, here according to this relation, it implies that the other side of the product, delta E, must tend to 0. That is, the ground state energy is sharply defined. There is no change of energy there. Okay, there is no change of energy, hence it is sharply defined. Now let us look into two types of interactions. Now in electronic transitions where the outermost valence electrons get excited and they move from higher to lower energy levels or from lower to higher energy levels depending upon whether it is emission or absorption. The lifetime of these excited electrons are, you should remember, it is 10 raised to minus 8 seconds, right? Now let us use this value in the Hasenberg's uncertainty principle, and we will be able to calculate that delta E is equal to h by 4 pi divided by delta T. So substituting the values for delta T here, we get the approximate value of 10 raised to minus 24. Here, let us look its value in terms of frequency. E is equal to h into delta nu. So delta nu is equal to delta E by h, and this gives the approximate value of 10 raised to 8 hertz. Now we know that the electronic transitions give radiation in the visible or ultraviolet regions, but the frequency range of those radiations are of the order of 10 raised to 14 or 10 raised to 16 hertz. Hence, this change of frequency, this 10 raised to 8 hertz, is not significant in this region. So even if there is a change in frequency, there is a spectral shift, there is a spectral broadening, it does not affect the spectrum in the visible or ultraviolet range. But in the case of electron spin resonance, we understand that the electron spin state has a lifetime of 10 raised to minus 7 seconds. So calculating the energy change delta E, here we get the value is approximately equal to 10 raised to minus 24 as earlier. And the frequency change here will be approximately 10 raised to 7 hertz. But this region of frequency in the spectrum, that is of the radio frequency region, it is of the order of 10 raised to 8 to 10 raised to 10 hertz. So this is comparable, right? In the radio frequency range, this delta nu, that is this broadening of 10 raised to 7 hertz, is very much significant in this range of 10 raised to 8 to 10 raised to 10 hertz. Hence, this will affect the ESR spectrum, electron spin resonance spectrum. So collision broadening, Doppler broadening, and Hasenbergs uncertainty principle are the factors that affect the spectral width of a spectral transition line. Now let us look into the factors affecting the intensity or amplitude of the spectral transition. First one is the probability for transition between the two states. There are certain selection rules that are to be obeyed, and according to those selection rules, only particular transitions take place. Okay. The next factor is the population of the energy states. Now, the ratio of population between two energy levels E2 and E1 is given by N2 by N1, where N1 is the population or number of atoms in the lower energy level, N2 is the population or number of atoms in the upper energy level. So N2 by N1 is equal to exponential of minus delta E by KT, where delta E is the energy difference between the energy levels, K is the Boltzmann's constant, and T is the temperature of the system. Now, only if there is sufficient number of atoms in the lower energy level will there be an absorption to the higher energy level. If there are no atoms or no molecules, that is, in effect, there is no sample, even if we give radiation upon it, there will be no change, right? So depending upon the population or number of atoms in each energy level will be the intensity of that spectral line. If more number of atoms are excited into the higher energy level, we will get a peak with higher intensity. If less number of atoms are de-exciting to a lower energy level, we will get a spectral line of lower amplitude. Now, the next factor affecting the intensity of that spectral line is the length of the sample and the concentration of the sample. We have the relation I by I naught equals exponential of minus KCL, where K is a constant for a particular spectroscopic transition, C is the concentration, L is the path length through the sample, I naught is the intensity of the incident radiation, and I is the intensity of transmitted radiation. Now, taking log on both sides, we can write 2.303 log of I by I naught is equal to minus KCL. That is log of I by I naught is equal to minus K by 2.303 into CL. In other terms, it is equal to minus eta CL. We can write transmittance as the ratio I by I0. That will be equal to 10 raised to minus eta CL. Hence, transmittance T is measured as 10 raised to minus eta Cl. Here, eta is the molar absorption coefficient or decadic extinction coefficient or decadic absorptivity. We can write this expression in terms of absorbance also. So, taking log of I by I naught is equal to minus eta Cl, the absorbance or the optical density is written as log of I naught by I, taking the reverse. Hence, we write absorbance A equals log I naught by I. That is A equals eta Cl. This is called the Beer-Lambert law. Now, usually we take the absorbance measurements in spectrometers. This is because the transmittance has an exponential relation with the concentration and path length, whereas the absorbance has direct relationship with concentration and path length. So the factors affecting intensity of the spectral line are the probability, transition probability between two states, the population of the two energy levels, and the sample path length and concentration. That's all for today's session. Thank you.